very complex build process, and you can see we use electronic models to direct the guys that are building the engine to make a nice smooth finish for the air flowing into the engine. So this really is the start of the process for our XWB engine.
Aviation burns through roughly 95 billion gallons of jet fuel every year. That's not just an environmental headache. It's a financial black hole for airlines and a ticking clock for an industry racing toward net zero emissions by 2050. While the world debates electric planes and hydrogen dreams, one engine sitting on a test stand in Derby, England, might already have cracked the code. It's called UltraFan, and it doesn't just promise incremental gains. It rewrites the rulebook entirely. So what makes this different from every other next big thing the industry has hyped before? The problem aviation can't ignore. Airlines are caught in a vice. On one side, fuel prices swing wildly but trend upward, eating 20 to 30% of every carrier's operating budget. On the other, regulators worldwide are tightening emission standards faster than manufacturers can adapt. The European Union's Carbon Border Adjustment Mechanism, ICAO's Carbon Offsetting and Reduction Scheme, and the looming 2050 net zero commitment aren't suggestions. They're mandates with teeth. Current engines are incredibly refined. The problem is, they've hit diminishing returns. Squeezing another percentage point of efficiency from traditional turbofan designs requires exponentially more effort and cost. Meanwhile, the industry's growth projections show global air traffic doubling over the next 2 decades. More flights, stricter rules, volatile fuel markets, something has to give. Enter sustainable aviation fuel. SAF can cut life cycle emissions by up to 80% compared to conventional jet fuel, but it's expensive and supply is limited. Even if production ramps up, today's engines can only handle blends up to 50% SAF without modifications. The infrastructure exists, but the hardware lags behind. Airlines need propulsion technology that doesn't just tolerate tomorrow's fuels, it's designed around them. That's where UltraFan steps in, not as a band-aid, but as a foundational shift in how engines are built. What makes UltraFan different? Most jet engines lock the fan and turbine together on the same shaft, spinning at the same speed. It's simple, proven, and increasingly outdated. UltraFan uses a geared fan architecture. A power gearbox sits between the fan and the turbine, letting each component spin at its optimal speed independently. Why does that matter? Because the fan wants to spin slowly to move massive amounts of air efficiently, while the turbine needs to scream at high RPMs to extract maximum energy from hot exhaust gases. Forcing them to compromise has always been a trade-off. The gearbox eliminates that compromise. This isn't a new idea. Pratt & Whitney's geared turbofan pioneered it commercially over a decade ago. But Rolls-Royce has taken the concept further. UltraFan's fan diameter stretches 140 inches, making it the largest aero engine demonstrator ever built. That size isn't for show. A bigger fan moves more air per rotation, which means the engine can generate the same thrust while burning less fuel. Pair that with a variable pitch fan system, think of it like a helicopter rotor that adjusts blade angles in real time, and you get an engine that adapts dynamically to every phase of flight. The result is an efficiency leap that doesn't rely on exotic fuels or radical airframe changes. It's pure thermodynamics and mechanical ingenuity, scaled up and stress-tested to the point where it's no longer theoretical. Rolls-Royce didn't just design UltraFan on computers. They built it, bolted it to a test stand, and ran it at full power. 25% better isn't just a number. A 25% fuel burn improvement over first-generation Trent engines sounds abstract until you do the math. A single wide-body aircraft on a transatlantic route burns roughly 3 gallons per hour. Over a 15-year service life, one plane consumes tens of millions of gallons. Cut that by a quarter, and you're talking about savings in the hundreds of millions of dollars per aircraft. Scale that across a fleet. A major carrier operating 200 wide-bodies could save billions over a decade. That's not just margin expansion, it's the difference between profitable routes and ones that get cut. It also means airlines can offer lower fares or reinvest in fleet modernization without bleeding cash on fuel hedging. Then there's the environmental math. aviation contributes roughly 2.5% of global CO2 emissions, but its impact on climate goes beyond carbon. Contrails, NOx emissions, and particulates all play a role. UltraFan's efficiency gains directly translate to fewer tons of CO2 per flight. On long-haul routes, where wide bodies dominate, a 25% reduction per aircraft could offset the emissions of hundreds of cars annually. This isn't about making aviation green, that's a much longer road. But it buys time. It turns the 2050 net zero goal from a fantasy into something airlines can actually model and plan for. And it does so without requiring passengers to accept slower, smaller, or less convenient air travel. The materials revolution, inside the engine. Efficiency improvements mean nothing if the engine melts under stress. UltraFan operates at temperatures and pressures that would obliterate older designs, so Rolls-Royce had to rethink materials from the ground up. The fan blades are made from carbon titanium, a composite that's lighter than aluminum but stronger than steel. Weight matters enormously in aviation. Every kilogram shaved off the engine means less fuel burned over the aircraft's lifetime. But strength matters just as much. These blades spin at hundreds of miles per hour, ingesting birds, ice, and debris without shattering. Deeper inside the engine, where exhaust gases exceed 20,400 degrees Fahrenheit, metal components hit their limits. Rolls-Royce turned to ceramic matrix composites, materials originally developed for spacecraft and gas turbines. CMCs can withstand temperatures 500 degrees hotter than the best nickel-based superalloys while weighing significantly less. That allows the engine to run hotter without needing as much cooling air, which improves overall thermodynamic efficiency. These aren't off-the-shelf parts. Manufacturing CMC turbine components requires precision layering and heat treatment processes that took years to perfect. The supply chain for these materials barely existed a decade ago. Now, they're becoming the standard for next-generation engines, and UltraFan is leading that transition. It's not just about performance. Durability matters too. Airline engines undergo brutal cycles, rapid temperature swings, corrosive high-altitude atmospheres, and thousands of takeoffs and landings. Advanced materials reduce wear, extend maintenance intervals, and cut life cycle costs. That's the kind of engineering that doesn't make headlines but changes everything operationally. Sustainable aviation fuel from day one. Most jet engines in service today were certified for conventional jet fuel, kerosene refined from crude oil. Sustainable aviation fuel made from waste oils, agricultural residues, or synthetic processes has a slightly different chemical profile. It burns cleaner, but compatibility isn't automatic. Many engines require modifications or are restricted to 50-50 blends. UltraFan was designed from its first KAD file to run on 100% SAF without compromise. That's not a marketing claim. Rolls-Royce has already demonstrated it during full-power ground tests in Derby. The engine's fuel system, combustion chamber, and seals are all validated for neat SAF, meaning airlines won't need special approvals or derating when they switch. Why does that matter now, when SAF represents less than 1% of global jet fuel supply? Because that's about to change fast. Governments are mandating SAF blending. Europe requires 2% SF by 2025, ramping to 70% by 2050. The United States is incentivizing production through tax credits. Airports in California, Scandinavia, and Singapore are building dedicated SAF infrastructure. Supply is growing, and prices are falling as production scales. But if engines can't use it, the fuel doesn't help. UltraFan future-proofs airlines against that bottleneck. When SAF becomes the norm, operators with UltraFan-powered aircraft won't need retrofits or workarounds. They'll just fly. That kind of operational flexibility has real value, especially as sustainability becomes a competitive differentiator for carriers. The demonstrator that proved it works. Testing a jet engine isn't like road testing a car. You can't just spin it up in a parking lot. Rolls-Royce built a dedicated outdoor test facility in Derby capable of handling UltraFan's massive size and thrust output. The demonstrator was mounted, instrumented with thousands of sensors, and subjected to conditions that replicate everything from takeoff thrust to cruise efficiency. In 2023, UltraFan completed its first full-power runs. Engineers measured fuel burn, thrust output, emissions, and thermal performance across the entire operating envelope. Then they swapped in 100% sustainable aviation fuel and ran the tests again. The engine didn't just tolerate SAF, it performed identically to conventional fuel, validating years of design work in a matter of hours. Ground testing isn't the finish line, but it's the hardest gate to pass. Engines fail spectacularly when design assumptions are wrong. Blades fracture, bearings seize, combustion becomes unstable. UltraFan's successful test campaign means the core technology works as intended. The gearbox, the composites, the fuel system, they all held up under real-world loads. Next comes endurance testing, thousands of simulated flight cycles to verify long-term reliability. After that, flight testing on an actual aircraft. But passing full-power ground tests with zero major issues is a massive validation. It moves UltraFan from promising concept to proven technology ready for application. Scalability. Across the entire fleet, UltraFan isn't just one engine. It's a scalable platform covering a thrust range from 25,000 to 110,000 pounds. That means the same underlying architecture can power everything from narrow-body single-aisle jets on short regional hops to massive wide-body aircraft crossing oceans. For Rolls-Royce, that's strategically huge. The company has long dominated the wide-body market with its Trent family, but it exited the narrow-body segment decades ago after struggling to compete with CFM International and Pratt & Whitney. UltraFan gives Rolls-Royce a credible path back in. Narrow bodies represent the largest segment of the commercial aviation market. Airlines operate thousands of Boeing 737s and Airbus A320s, and both manufacturers are planning next-generation replacements for the 2030s. If UltraFan's technology proves out, Rolls-Royce could bid on those future platforms with an engine that offers unmatched efficiency across the board. Scalability also simplifies maintenance and training. Airlines prefer commonality. If mechanics and pilots are familiar with one engine family, adding another variant is far cheaper than introducing an entirely new design. UltraFan's modular architecture means operators could potentially maintain both wide-body and narrow-body fleets with shared tooling and expertise. That's not just a technical advantage, it's an economic moat. Once an airline commits to an engine platform, switching is expensive and disruptive. Scalability locks in customers across multiple aircraft types for decades. Why airlines are watching closely. For airlines, engines aren't gadgets, they're 20-year investments. A new wide-body costs upwards of $300 million, and engines account for roughly a quarter of that. Operators don't just look at fuel efficiency, they evaluate reliability, maintenance costs, resale value, and manufacturer support. UltraFan's 25% efficiency gain is compelling, but airlines want proof it won't spend half its life in the shop. Rolls-Royce has built a strong reputation for engine reliability with the Trent XWB, one of the most dependable wide-body engines in service. UltraFan builds on that heritage, but with newer materials and architecture, so airlines will scrutinize early adopters carefully. Then there's the sustainability angle. Passengers increasingly care about emissions, and corporate travel departments are factoring carbon footprints into booking decisions. Airlines that can advertise significantly lower per-seat emissions gain a marketing edge. UltraFan's SAF compatibility and fuel burn reduction offer exactly that differentiation. Upfront costs matter too. Next-generation engines command premium pricing, but airlines can offset that through lower fuel bills and longer maintenance intervals. The real question is payback period. If UltraFan-powered aircraft break even on costs within 5 years and deliver savings for the next 15, the business case becomes irresistible. Operators are also watching how Rolls-Royce structures support contracts. Modern engine deals often bundle maintenance, parts, and performance guarantees into a single package. Airlines want certainty, and manufacturers that can offer predictable, all-in pricing win deals. The competitive landscape and Rolls-Royce's return. UltraFan doesn't exist in a vacuum. Pratt & Whitney's geared turbofan already flies on Airbus A320neo and A220 families, proving the geared fan concept works commercially. General Electric and Safran are jointly developing the Rise program, targeting open rotor designs that promise even greater efficiency, though with noise and certification challenges. Rolls-Royce is playing catch-up in the narrow-body market, but UltraFan's technology might leapfrog the competition. While Pratt's G12 has faced durability issues requiring costly fleet-wide inspections, Rolls-Royce has the advantage of learning from those problems. UltraFan's materials and gearbox design incorporate years of lessons that early GTF operators paid for in downtime and delays. GE's RISE program is ambitious, but open-rotor engines are louder and face regulatory hurdles. UltraFan uses a conventional ducted fan, meaning it's certifiable under existing frameworks and compatible with current airport infrastructure. That's a huge advantage when speed to market matters. Strategically, UltraFan also positions Rolls-Royce for future engine competitions. Airbus and Boeing are both planning next-generation single-aisle aircraft for entry into service in the mid-2030s. Those programs will define the narrow-body market for the next 30 years, and engine selection is a multi-billion-dollar decision. UltraFan gives Rolls-Royce a seat at that table for the first time in decades. Winning even a fraction of the narrow-body market would transform the company's financials. Right now, Rolls-Royce derives most of its civil aerospace revenue from wide-body engines. Adding narrow-body exposure diversifies risk and opens access to a much larger fleet. What this means for future aircraft. Engines and airframes evolve together. When Rolls-Royce or its competitors deliver a step change in propulsion, airframe manufacturers redesign wings, nacelles, and fuselage structures to maximize that advantage. UltraFan's efficiency and size will influence how the next generation of aircraft looks and performs. Larger fan diameters require either higher landing gear, so the engine clears the ground, or creative nacelle integration. Airbus and Boeing both have design teams working on configurations that optimize UltraFan-class engines. Expect to see tweaked wing mounts, redesigned pylons, and aerodynamic refinements tailored to these power plants. There's also talk of hybrid electric architectures, where an engine like UltraFan provides primary thrust, while electric motors assist during takeoff or taxi. That's still experimental, but UltraFan's modular design and efficient core make it a natural candidate for such integration. Beyond commercial aviation, military and cargo operators are watching. UltraFan's fuel efficiency could extend the range of tankers and transports, while its SAF compatibility aligns with defense sustainability mandates. Rolls-Royce has a strong military engine business, and technology transfer between civil and defense programs is common. Ultimately, UltraFan's legacy won't just be one engine. It's the technology foundation for a generation of propulsion systems that bridge the gap between today's kerosene-burning turbofans and whatever comes after, or something we haven't imagined yet. For now, it's the most credible answer to aviation's efficiency and emissions crisis, and it's already running.